If you've ever had to lie in an MRI machine for some medical diagnosis, you may have asked yourself, how is it that this can see inside my body? Just what is it that they're measuring and why? As it turns out, the answers to these questions go to the heart of some very fundamental physics. At the core of MRI is nuclear magnetic resonance, or NMR. Instead of jumping into NMR directly, it'll be helpful to review the physics which makes the measurement technique possible. At the heart of NMR is spin. In classical physics, objects can rotate about an internal axis to have angular momentum. In quantum mechanics, particles are point-like and cannot rotate, but we still observe them to exhibit an intrinsic, indivisible angular momentum, which we call spin. Just like electrons have charge and mass, they also have spin. But what is it that spin does exactly? Well, it is responsible for many of the magnetic interactions of particles. Particle spins generate and respond to magnetic fields just like little magnets. Particles can also interact magnetically via their orbital momentum, acting like little current loops. Most commonly, we look at spin half particles, where the spin can take one of two values, which we call spin up and spin down. Electrons, protons, and neutrons are all spin half particles. However, spins tend to combine in complicated ways. For example, although a proton and neutron are both spin half, together they form a spin 1 deuterium atom with three possible values. As another example, the most common form of carbon, carbon 12, is composed of 6 protons and 6 neutrons, but has zero spin. But adding one more neutron, carbon 13 becomes spin half again. When spin half particles are far from any magnetic fields, spin up and spin down have the same energy. However, when put in a magnetic field, these energies split, becoming two distinct levels. Spin 1 particles form three levels. Importantly, see that spin 0 particles do not form different levels in magnetic fields, and so you cannot directly distinguish their states. If a particle is in the lower level here, we can get it to the upper level by giving it the right amount of energy. According to quantum mechanics, this will depend on the frequency of the light. Now, there's one more thing we need to discuss if we want to turn these concepts into a measurement technique. If we had a system of various hydrogen atoms in some molecule, they would all split the exact same way. Many different molecules would all be indistinguishable. Although all the nuclei split the same in isolation, the hydrogen atoms will have different electron configurations in different molecules. The moving electron charges in the vicinity of these groups will create a magnetic field from their spins and orbits that effectively dampens or shields the nuclear spin. Compare this ethane molecule to this propane molecule. These CH3 groups are identical in their vicinity, and so the electrons will arrange themselves in the same way. However, they are not locally the same as these CH2 groups, which will arrange themselves differently. Different electron configurations will lead to different energy absorptions. Now that we have all that background, the basics of NMR should be straightforward to understand. To simplify, we will only look at proton NMR, where we are only really looking for the spectrum of hydrogen groups in molecules, since C12 and O16, as the most common isotopes, are NMR silent. Say we have this molecule of propane and want to look at its NMR spectrum. We will first put it in a steady magnetic field to split the energy levels. Each group will have different splitting depending on their nuclear shielding. We now excite the system with light and look at the frequency spectrum. We can associate each peak with a different electron environment in our sample. Here, we would see two main peaks. corresponding to the CH3 and CH2 groups. You'll notice that with a high resolution, you can see a kind of substructure among these peaks. This is in fact due to the interaction of spins with each other, rather than with the external magnetic field. In more sophisticated NMR experiments, this data can give you additional information. Let's compare two similar NMR spectra. Consider this molecule of butane and this molecule of 1-propanol. If I show you two unlabeled spectra, can you guess which is which? There are only two kinds of local groups in the butane molecule. Since the CH3 groups in both molecules look the same, we should expect similar NMR peaks for them. Similarly, the CH2 groups look the same in both molecules. However, this CH2 and this OH group in 1-propanol look different locally, so we should expect two new peaks. This is the spectrum for butane, where this peak represents the CH3 groups, and this peak represents the CH2 groups. And this is the spectrum for 1-propanol. Just as we predicted, there are similar CH3 and CH2 peaks, with two new peaks for OH and the other CH2. As we saw in our examples, NMR can be very important in the analysis of organic chemistry for identifying and mapping molecular structures. Owing to its fundamental connection with magnetic and atomic physics, NMR has even found a place in condensed matter experiment. And, back to what we began with, NMR is the basis by which MRIs can look inside your body using very strong magnetic fields. So next time you wonder why you can't wear your earrings or jewelry into an MRI, you'll know the reason. Thank you for watching.